stuff that still fits. So I'm going to tell some stuff that still fits title, but is going to be mostly about young tableaus and the stuff related to algebraic combinatorics. So let's see. So thank you, Rick, for inviting me. And the picture on the lower left is maybe the most unusual memory from Yale. That's where I went from time to time when I felt especially vigorous. So let me, and the building on the upper right corner is where I go to concerts when they're gonna open eventually. Okay, so what I'm going to talk about is some inequalities related to algebraic combinatorics, and I'm going to start by telling you about dimensions of reducible representations of the symmetric group. And f lambda is a number of standard Young tableaus of shape lambda, which is also character of dimension of the character of the reducible representation corresponding to lambda. Let's try this. Is everyone okay with this? Yeah, so do this if you're okay, and get some other crying emoji if you can't voice yourself. And I encourage everyone to be on camera because I actually can see you on my big screen TV. So let's denote by dn the maximal dimension of the reducible representation, and it's a rather classical question. What is dn? Dn there's a finite number of reducible representations correspond to partitions, so one can ask about asymptotics. And so I figured I'll tell you a little about the history because the history is rather amusing. So the whole story started in this paper by Bivens, Metropolis, Stein, and Wells, who decided that in 1954 they're going to compute characters of the symmetric group of degree 15 and 16. Now, from sort of modern point of view, there is absolutely no reason to do that. And they had really no reason to do that either, except I think they were curious. So this is what really happens. On top, you're going to see a quote from the original paper. And basically, what happened is they built this Maniac computer, which was one of the first modern computers, the one that uses von Neumann architecture. And they built it at Los Alamos to do some nasty calculations as part of the Manhattan Project. And this is what they taught the computer to play chess, do Monte Carlo simulations for fun. And another thing that they thought was fun is to calculate characters of degree 15 of S15 and S16. They said that they checked 14 and 13 just to make sure that this is all correct. And everything seemed to work out. So you see Stein and Metropolis right in front of this giant computer on the left. The computer used tubes and stuff. I don't actually know what was going on in that computer, and it weighed about 1,000 pounds. And so as I said, it started with that paper because that paper had a footnote. The very last footnote of the paper says, we're really interested in finding what is the largest value of the dimension of the reducible representation. And we couldn't find this problem in the literature, but they believe this is of some practical interest. I find that a little bit of a stretch, but I would say it's of theoretical interest. So everyone good with this? Any questions about the history? Okay, good. So
I have a question.
Go ahead.
So yeah, what you're saying it basically is all this stuff that we know nowadays about the symmetric group is just recent. These guys didn't know all that young diagram one.
No, I mean there were no really computers before that. A number of partitions of 16 is already beyond what you can do on a piece of paper. So yeah, that's that really we really don't know that much. And in fact, what people got from simulations wasn't that from computations wasn't that great either. I'll show you in the next slide or a couple of slides. So there is something that you can figure out fairly quickly is using Bernstein formula, which holds for every finite group, but in particular for a symmetric group, sum of the squares of the dimensions equal to n factorial. So that by itself implies that the maximal dimensions at most square root of n factorial and at least square root of n factorial divided by the number of terms, which is p of n. And since p of n is rather small number of partitions compared to square root of n factorial, that gives you 2 terms and the asymptotic. So that's already pretty good and you didn't actually start to do any work. Let me mention a conjecture. So this is what you can get by doing almost nothing, and you immediately get to conjecture. What is the next term in the asymptotic? And this is Versche-Kerov-Pass conjecture, which says that the next term in the asymptotic should be c times square root of n for some non-zero c, and that's actually open. It's been open for about 35 years. So trivial stuff, a conjecture. There's nothing in between, really. Everyone good with that? Any questions about any of this? Okay, so now let me get to the data. This is so people really started computing that, and by people I mean just one person. I'll show you this person in a second. So if you open OIS, one of the earliest sequence is the sequence 3040, which basically lists the highest degree of reducible representation one by one, and if you look at the graph, you see that it grows indeed like 1/2 n log n, and the last number that's computed is so number of partitions. So it's for 81. In that case, there are actually 18 million partitions of 81, and here is the precise partition which maximizes the dimension. So this was computed by John Mackay and notice the date. So this was 1976. Again, not a recent computation. And let me show you. I think I forgot to erase that. So the way he did it on this antiquated PDP computer which had 12-bit microprocessor. You can figure out, you would think that by now this was made by DEC back in the day, and John Mackay did a lot of computations. So just to be clear, he used the Hookland's formula for the dimension. Hookland's formula was known since the early 50s, and in fact, Metropolis used an equivalent version to the Hookland's formula, which was proved by Weil earlier. So it was not a big deal. Computing that number for a particular partition is easy. It's just that there are lots of partitions for which you have to do it. And presumably now people could have done more, and they have done more, except that they were not particularly successful. So there are no precise numbers from this point on. However, people have started looking at random partition. Can I move on? I didn't ask. Any questions about this? Okay. So when you look at a random partition, there is actually a way to sample random partition according to this distribution, the square dimension divided by n factorial. This is what we've seen in the Bernstein formula, and the way you do it, there is something called Robinson-Shenstedt correspondence, which allows you to plug a permutation and get a shape of a partition corresponding to that permutation. And you can try doing that, and here is these are pictures from Dan Romik's book, which I cut and pasted. So this is n equal to 100, and this is n equal to 1000, and you see that the curve is starting to emerge. That's a famous curve that was computed precisely later, but you can see the curve, right?
Yeah. Okay.
And here is the curve. The curve, this is what's known as Versche-Kerov log and Shep. Log and Shep computed in 77, and Versche-Kerov used a completely different approach to compute this in 81 independently. There is a formula with arctangent one can write, but here is a kind of nice way to parameterize the curve by an angle theta between minus pi over 2 and pi over 2, and it's just sum of trigonometric functions. It's not anything particular that you would recognize right away, but it's sort of hard to see here. But it goes from 0 to 2. So the area under the curve is supposed to be 1. So it's like 1/4 of the 2 by 2 square. Okay, 1/2 would be exactly the triangle. So it's a kind of nice, nice shape of 1/4 of a square. And is everyone good here?
I have a question. Is this shape supposed to emerge kind of probabilistically from random partitions, or is this what the one with maximal dimension is? Like?
No. That's a really good and difficult question. In fact, the shape is the same, but the way they computed it is by using by using the Hookland's formula. So essentially, you set up you use the Hookland's formula to set up a certain variational approach, and which allows you to calculate the shape. But that's the shape for a random partition. That's not the shape for a maximum. But because they can, using that shape, you can calculate the dimension, and turns out that the dimension is close enough to square root of 1 factorial. And then you can prove that everything that's close to that shape has to be everything that's close to square root of 1 factorial has to have that shape. So I'm sort of collapsing multiple theorems into one.
So this gives you both upper and lower bounds in the end, or just lower bounds?
For d of n? For what?
For the maximal dimension.
For the maximal dimension, we already have upper and lower bounds. I forgot. I think I wrote that before. Yeah, for maximal dimension, we already have upper and lower bounds.
I'm just trying to understand, how do these random shapes interact with what you know about these bounds? Do they refine them, or what?
How do so partitions have certain number of Young tableaus, so partition correspond to a character which has dimension. Yeah. Now the claim is that the maximal will have that shape, but not only the maximal, the random with respect to this Plancherel measure. I didn't want to say these words.
I see.
So you don't take uniform partition, you take that specific partition.
Okay.
Partition corresponding to a Plancherel measure, and then you get this shape. And by getting this shape was on a scale square root of n by square root of n. So there's some error terms. And it's so the maximal is sitting somewhere within, let's say, cubic root of n. In fact, it's a little closer than that, but doesn't matter. So it's a little unclear if the maximal even has a well-defined shape in terms of lower order terms. But on the first level, that's the shape. Did I answer your question?
I think so. I mean, I'm getting the impression that knowing this theorem about what the shape has to do, about the shape, implies that you get upper and lower bounds on the, you get that error term of little o of root n out of this, right? Is that what you're saying?
No. Little o of root n is open.
Oh, sorry, the big O of root n, maybe.
Big O, yes, you're good.
Okay. Now.
And that particular big O disappeared at 0. So in fact, because the number of partitions is very small, the dimension is going to be very close to square root of n factorial. Dimension of almost all of those representations. Almost all random representation, in particular the maximal one. It cannot be larger. So I want to mention that there's a follow-up paper by Verchik and Kerov, which actually does something interesting. So the lower bound here is the same as the lower bound I showed before, coming from Burnside formula. But the upper bound is saying that there is a way that there's a way that maximal dimension is bounded away from the square root of n factorial. It's bounded away by some e to the square root of n, by some constant to the square root of n. And that's highly non-trivial, and that follows from analysis of the shape. And to be more precise, follows from the proof which goes into that shape.
It kind of sounds, if I can interrupt, when you present it like this, it sounds like the most interesting object is the, not the maximum shape, but just the random shape, right?
Maximum for many people it is.
Yeah.
But I want to talk about the maximum.
Okay, fine. Sorry.
Yeah, but it is true that lots of people think the random is more important actually than the maximum. And I want to say that Vershik and Pavlov did simulations, which I don't believe at all. They have some kind of strange idea of how to calculate the C. The C is what should be the order. It should be square root of n factorial times e to the minus constant times square root of n. And they believe that C should be 0.91. And I don't think their simulations are right. But that's all we have. They don't write actually on which computers they do it. I'm assuming it's some kind of laptop running Microsoft Windows or something like that. This is relatively recent. This is about 2010. Okay. Can I move on? So my next objects are Littlewood-Richardson coefficients, which are structure constant of the ring of characters of GLN. And you can, if you don't know anything about characters, maybe you know Schur functions, and you multiply two Schur functions. You write them in terms of in the basis of Schur functions, and you get some non-negative integer C lambda menu. And the question is, what can be said about them? And one important thing to say is that it actually is a number of, they have a combinatorial interpretation as a number of certain young tableaus of shape lambda minus mu, and the content is new. And by the content, I mean, if your new is 4, 3 to 1, that means that you put 4 inside, and 4 1s, and 3 2s, and 2 3s, and 1 4. And in addition, they have to be ballot sequences. So until every point, there are more 1s and 2s, at least as many 1s as 2s, at least as many 2s as 3s, and so forth. So that's a combinatorial interpretation for Littlewood-Richardson tableaus. We're not going to use them, but it is important there is one, because because having combinatorial interpretation actually is quite handy. So Stanley rather recently had the following result that if you look at all possible Littlewood-Richardson coefficients, remember Littlewood-Richardson coefficients, size of lambda has to be equal to size of mu plus size of nu. So the only parameter here n he is using, and what he's saying is that if you look at maximal of all possible Littlewood-Richardson coefficients, that maximal it grows exponentially, roughly like 2 to the power n over 2. So that is possibly quite surprising, and I wouldn't know how to prove it right away, except the way he concluded is by looking at there is sort of analog of Burnside identity, which is this Harris-Williams-Bring identity, which gives you a generating function for squares of Littlewood-Richardson coefficients. So you raise q to the size of mu, t to the size of nu, and you sum over all possible lambda mu, and that turned out to have a nice product. Proving that is a little more than an exercise, but not super hard. It's about half a page. Okay, and once you have the generating function, then you can just substitute q equal to t equal to 1, and from that and a little bit of analytic combinatorics, which was done before Stanley, you can make a conclusion, Stanley's theorem. So we were somewhat puzzled about that, and we wanted to generalize it and understand it further. So we defined the C and K, which are maximals of Littlewood-Richardson coefficients, but notice that there are 4 maximal here and only 3 maximals there. That's because there is only one parameter n here, and there are 2 parameters n and k here. And then we showed so I still can't believe we were the first to prove the upper bound. That's a very clean upper bound that this largest Littlewood-Richardson coefficient is at most square root of n choose k, and it's at least square root of n choose k times again e to the big O of root n. So some number of partitions goes into here. And the way we do it is by finding completely different analogs of Bernstein identity, which kind of work for our purposes. On the one hand, that's actually really easy to prove. On the one hand, the sum of the square, if you fix mu and nu, the sum of the squares of Littlewood-Richardson over all lambda is at most n choose k. And in a different direction, sum of the squares over all triples lambda mu and nu is at least n choose k. And that if you put them together, that immediately gives you 0. Everyone good? Everyone good with this? So there is a reason when we had for doing that. And the reason is these questions that Stanley asked, what are the shapes that achieve the maximal? And turns out that those are the same Verschakerov-Logan shapes as you've seen before. With formula, I'm not even, it says formula, but it's still somewhat informal. Basically, we're saying that for every pairs of partitions mu and nu, and by pairs, I mean sequences of partitions which converge to Verschakerov-Logan shape, there's a sequence of lambda of the same shape for which everything works out. And so notice the difference. For the maximal dimension or average or random dimension with respect to a Planck measure, you get the Verschakerov-Logan shape. But for maximal Littlewood-Richardson, the implication goes in only one direction. So in fact, we don't actually believe that it goes in the other direction. That we cannot disprove that, but I don't think that's true. So in fact, we conjecture that sometimes you can have partitions which you would think. So there's one condition is missing. The conditions that Verschakerov-Logan shapes. So sometimes you get a much smaller Littlewood-Richardson that you would expect to get, even if they have the right shape. So that doesn't happen. That doesn't happen in the Verschakerov case, in the case of the dimension. So that's.
Can I ask a question?
Yeah.
So there's no k in this theorem, right? It's just the the 4 maximum case.
So there is a k here. In here, it's a conjecture. So
what's the conjecture? I don't see any k on this page.
Yeah, because I decided to simplify it. So basically, k is equal to n over 2 in this case.
Oh, I see. Okay, I got it.
So that, yeah, so that is k.
But if you fix k to be some other multiple of n, then it's the same.
Well, then you get whatever is going to be in the asymptotic of n choose k. It's going to be a different constant. So kind of like the entropy constant that you get.
I understand.
So there is one thing I want to mention before I move on away from Littlewood-Richardson coefficient is just to say that it's very important to have combinatorial interpretation. So if you define, if you instead of looking at the maximal Littlewood-Richardson like the way we did before, let's look at just partition lambda which have L rows. that's already kind of interesting. And in this particular case, we get a really nice result. So basically, the asymptotics is going to grow like square of the number of rows times log n. I put the subscript L sub n just to indicate that Ln, so number of rows, can also grow with n. So it just should be little o of square root of n. And the way we prove that is by, so there are upper bound and lower bound in this asymptotics. And both lower upper bounds use combinatorial interpretation. The lower bound, the upper bound uses a different combinatorial interpretation of Littlewood-Richardson that I explained to you. The upper bound uses Bernstein-Levinsky patterns, which are this kind of triangles. They're kind of funny. So if you look, if you have a good eyesight, you can see that 6 minus 5 is 1, which is the same as 2 minus 1, 4 minus 3. So around each hexagon, the differences along diagonals are always the same in the prescribed order. So that is kind of amazing. So Bernstein-Levinsky triangles of these patterns of this kind are basically an arrangement of numbers with given boundary, and you put inside numbers so that they satisfy this this equality along every hexagon. That is the idea, and you use that to get you use this combinatorial interpretation to get an upper bound for the maximal Littlewood-Richardson coefficient, and the lower bound uses a completely different combinatorial interpretation using Knudsen-Tau puzzles with marginals lambda mu. This is kind of, I thought this is the most symmetric version you can have. It sort of corresponds to, this particular one corresponds to C 3 to 1 to 1 to 1. When you have, so it turns out that there is a combinatorial interpretation using some kind of pieces or tiles which you can put together so that they match according along the curves. And so you use partitions to read off the boundary of the triangle, and then you put the puzzle pieces so that they're going to match. So the number of ways to do it turns out to be also number of Littlewood-Richardson coefficients, and that is the combinatorial interpretation Knudsen and Terry-Tau used to prove the saturation conjecture and a bunch of other things about related to this problem. And let me open up this. So the point that I want to make is that you need a combinatorial interpretation. If you don't have a combinatorial interpretation, it's really hard to make any progress in any of these problems. Are there any questions about any of that before I move on to something else? No. Okay. So the next one I want to talk about Kronecker coefficients, and those are structure constants in the ring of characters of symmetric group, where what you do with character of a sun is just multiply them. Just multiply two characters as functions on the group, and then you get another function, and you can write it corresponds to tensor product of these representations. And then you can write it in terms of reducible characters, and you get some numbers. Okay, so these numbers are, you know, because the definition is somewhat asymmetric, but you can write it in a symmetric form as 1 over n factorial triple, you know, sum overall permutations of the triple product of characters, which implies that really this Kronecker coefficient are symmetric with respect to switches between lambda, mu, and nu. You see what I mean? So they're nice combinatorial numbers, and you would want to understand what they are. And so, as I said before, having combinatorial interpretations are important, and in this case, there isn't any. There isn't any in a sense that it's been open for about 80 years. to give a combinatorial interpretation for Kronecker coefficients, and very few special cases for which this is known. And basically, I personally don't believe there is anything at all.
These are not related to Littlewood-Richardson coefficient somehow?
Oh, they are. That's why he made a conjecture just before Littlewood-Richardson coefficient were discovered to have a combinatorial interpretation. So in the special limit case, they are Littlewood-Richardson coefficient. So I can tell you exactly how it works, but yes, Littlewood-Richardson coefficients is a special case of Kronecker coefficient if they have sort of very long first row. That is Murnagan's main observation, so to speak. Just like before, I want to talk about the maximum Kronecker coefficient. So Stanley found, but never actually published or even gave a hint of how he would go about proving that. He basically said, well, you know, everyone should think about that. So, if you look at all possible lambda minus and look at the maximal Kronecker coefficient, turns out that according to him, it's basically the same as the maximum dimension. There is the same square root of 1 factorial going on. So we thought that we would prove that as well. Is everything I'm saying clear? Any questions at this point? I'll wait for a couple of seconds. Okay, so we wanted to actually give a proof of that result. And it turns out that one direction is really, really easy. This is the only thing I can actually prove in this talk. So I'm gonna show that the maximal Kronecker coefficient is at most the maximal dimension. And the way you prove it is by realizing that the Kronecker coefficient is bounded by product of dimension divided by another dimension, right? Because you take tensor product of two representations and write in terms of the third. But because of the symmetry, you can always multiply to smaller and divide by the larger. When you do that, you conclude that Kronecker coefficients are bounded from above by the smallest one. You see what I mean? So that immediately implies upper bound that you get square root of 1 factorial, which wasn't immediately obvious, but that argument actually works for any finite group. And in the opposite direction, you need another analog of Bern-Side identity, and we proved the following. We proved that the sum of the squares of Kronecker coefficient is basically n factorial up to lower order terms. So that argument is a little hard. But once you have that, you can conclude that in fact, in order to have in order to attain the maximal Kronecker coefficient, all three partitions have to have Verschach-Kerr Lagrange shapes. And again, we don't believe the inverse is true, but that's all we can prove. Is this clear? Questions about any of this? So let me tell you a little bit about the bounds. So the problem with Kronecker coefficient is not having combinatorial interpretations. So getting any bounds is actually quite difficult. So one bound is something we proved just recently. It's a very simple bound. Turns out that Kronecker coefficient is bounded from above by a number of three-dimensional contingent tables with marginal lambda, mu, and nu. And by that, I mean the following. So you take a box and you consider all this kind of three-dimensional matrices with integer entries, which are non-negative integer entries, so that the two-dimensional sums kind of orthogonal to each coordinate are either have lambda marginals or mu marginals or nu marginals. Okay. Yes, Rick?
Sure.
You want,
sounds
you
like
want
you're
to
giving us sounds like you're giving us a combinatorial interpretation, except that it's not quite right because there's only an inequality, right?
That's correct. It's very far from right. And in fact, we don't really know how far is it from right, but having that as an upper bound already gives you something that was unexpectedly strong for people in the area. So that using some existing works on counting number of contingency tables, which was initial polynomial method kind of introduced by Barvinak, and using some more of kind of real analysis in terms of kind of extending his approach, we actually were able to obtain a very clean upper bound. But because that upper bound actually uses only the length, the number of parts in each partition, it's the best when the partitions are basically all parts are the same, because it doesn't take into account smaller part. So if you have, if all you know about three partitions is the number of rows in each, then we get an upper bound, which is just this kind of really strange product of powers. And this is a little hard to get your head around that. So let me give you an example. Suppose you have all three partitions are rather long rectangles. So the rows are L square and number of rows is L. So they're all the same three partitions. This is both lambda, mu, and nu. Then in this case, the upper bound using dimension is actually about a cubic root of n factorial. That's pretty large. While our upper bound gives 4 to the n. You see what I mean? So we get a substantial improvement in that particular case. Now the problem is we do believe that that's also lower bound up to lower order terms, but we can't approach this problem at all. We have no idea how to do that. Not having a combinatorial interpretation gives us nothing to work with. So let me.
Can I?
Any questions about this?
Yeah. Is it even sort of algorithmic to be able to compute this?
I'll get to that. Okay. Basically, no. I mean, you do have a definition. Let me see where.
I know the definition, but is there
you do have a definition in terms of you can calculate it that way using characters. And sure. Characters, even on maniac computer, people computed characters. So very small Kronecker coefficients you can compute right away, but large ones you cannot.
I see. There's a conjecture here that it's not even in sharp P.
That's correct.
Okay.
But that's not. We'll get to that. I have a couple of slides at the end on the complexity. So let me just tell you how embarrassing this field is. This is a field in which I go to conferences. I wouldn't say that this is my main field. So take a staircase shape. So just this nice triangular shape over there. And the conjecture would be that the Kronecker coefficients in this case are really large, just about square root of n factorial, just almost like almost the same as if this were maximal dimensional representation. We cannot approach this at all. The best lower bound is greater or equal to 1, and that's highly non-trivial. And by highly non-trivial means it uses an interesting idea that doesn't generalize to other shapes. And so there's more to the story. There is Saxel conjecture, which he made when he was visiting UCLA. Which says that, in fact, Kronecker, when you take two staircases and another one and the third one can be anything, then all of them are greater than 0. But we are nowhere close to understanding that there are a bunch of special cases for which Saxel conjecture is known to be true, but it's basically open. Everyone good with this slide? Okay. So now, now let me tell you a little more about complexity. First of all, as I said before, dimension of characters can be computed in polynomial time. On the other hand, already Littlewood-Richardson coefficients are sharply complete, and that means that they probably not be possible to compute in polynomial time. This is for the input in binary, and it's open and unary, but it's probably going to be true also. Input in unary means it's actually going to be presumably exponential n, not just in number of bits in your part sizes. And in fact, this is the most interesting line at the end. Deciding whether Kronecker coefficient is 0 or not is already NP hard, even when the input is in unary. So Kronecker coefficients are really super hard. So proving that something is strictly greater than 0 is actually difficult, not a surprise with this Bessenrath-Benz paper. And in fact, you should understand that Kronecker coefficients lying in the class gap P, which is a difference of two sharp. So the way to think about it is there are two combinatorial. So Kronecker coefficients are differences of two combinatorial numbers, one with positive and one with negative. So those are again these three-dimensional contingency tables, and you're summing over a large number of permutations, triples of permutations, and you're adding or subtracting something to the marginals. And turns out that the ones with a positive give you a positive function, while the negative sign give you a negative function. And so the difference of those two gives you Kronecker coefficient. And notice that there's no 1 over n factorial here. That's important. So you don't divide, you just add and subtract. And so naturally one can ask are there any other questions other than Kronecker coefficients for which we know that something doesn't have a combinatorial interpretation? And that's something that I can tell you about. So the corresponding problem for character symmetric group has been known to be sharply hard for a long time. That's for even when the input is in unary. So the Nakayama rule, in the same way as before, shows that it's a difference of two Sharpe functions. Nakayama rule basically says that the characters are equal to number of Rim-Cook tableaus of this kind minus number of Rim-Cook tableaus of that kind. It's a very similar in nature rule. And what we proved is that this is something that I'm writing and should appear soon enough. So it turns out that the square of the character, deciding whether it's 0 or not, is hard. Let's just ignore what this says. It basically says that it's as hard as deciding whether square of a gap function is 0. And so presumably there is no, unless polynomial hierarchy collapses, there is no combinatorial interpretation for the square of the character. So I know that was a lot of computer science. Let me just show you the last little problem. Am I running over time, Rick? Are we good?
No, you have time. I mean, there's at least 5 minutes left, up to 13 minutes.
Okay. Okay, good. So I have I think 2 more slides. Are there any questions about any of this?
Yeah, I'm confused.
Yeah, go ahead.
The character is a number.
Yes, that's correct.
Why is it hard to show that its square is 0? And what do you mean the square is 0?
So it's a decision problem. I'm giving you lambda and mu, and you need to decide, is the character 0 or not? If you look at the character table of the symmetric group, there are a lot of zeros. It's actually unclear if majority of entries are 0 or minority. There are people who are arguing about that. But the question is computational. Is the number 0 or not?
Sure. Why did you put the square in there?
No real reason except it sort of comes up here.
And yeah, I didn't understand what gap P means. Did you explain that?
Yeah, so gap P is written here. It's a difference of two sharp P functions.
I don't, but if you have two functions, both are in sharp P, then isn't gap P in sharp P as well? You can compute each one. I don't understand.
No. Gap P is a difference. Gap P can be negative, just like characters.
Oh, you mean it's equal to the difference, even though you don't know what those two.
So these are not numbers; these are classes. So let
does it mean to take the difference?
Let me give you an example. Take a graph. If you have a graph, take the first function is the number of Hamiltonian cycles. The next function is the number of streak colorings. The difference can be positive and negative or whatever. But that difference is a function of a graph.
Yes.
The question whether this difference is zero or not is supposed to be hard.
But if you could find two functions, f1 and f2, both of which are computable, and the function you're looking for is the difference, then the thing is computable.
Yeah, so what we're saying is that character square is actually very hard to compute. We know that already, but we're saying that deciding whether character is zero is also very hard. So presumably there is no, let's take character square. That's a function in gap P. Yeah. When you take a difference, you square it. It's still a difference of two sharp P functions.
Yes.
So it's always non-negative. So presumably, one can ask, does that have a combinatorial interpretation, the character square?
Oh, I see. Okay.
And we're saying no. And that's the closest result that we can get to Kronecker.
Okay.
So the final thing I want to say is about bubble sorting and Brouillard order, and that is the following thing. So if you have two permutations, let's say you have one permutation is 3, 1, 2, and the other one is 1, 3, 2. 1, 3, 2 is smaller than 3, 1, 2 because when you start doing bubble sort to 3, 1, 2, you can go through 1, 3, 2. So formally, the way to write it is that sigma is equal to tau times the product of adjacent transpositions, which increases the number of inversions each time. Okay, but in terms of a picture, so that permutation is bigger than this permutation because you can multiply by this transposition and get from one to another on your way to identity. You see what I mean? So so that's how weak Brouillard order is defined, and we're asking and we're looking at the following number. That number is number of permutations. So given so if you fix a permutation, what is the number of permutations that are smaller than that one in this weak order? So how many possible permutations you can pass through on your way to identity? That is the formula. It's called the size of the order ideal in this weak Brouillard order. Is the definition clear? Yeah. So so this has been an open problem for about 30 years. Recently, we showed that with the students that it's sharp P complete, but that's not what I want to explain. I want to explain the Sidorenko theorem. Sidorenko theorem says that turns out that if you write sort of barred permutation in the opposite direction, then this number times the number for barred permutation of these sizes of orders is at least n factorial. And that's turned out to be a very general result. However, all the proofs are difficult. The original proof used combinatorial optimization, and recently Christian Gaetz and Yibo Gao found a different proof which generalizes to other root systems, but still rather difficult. So this is the final slide. So what I can show is that in this case, you actually do have a combinatorial interpretation. So what I'm saying is that in this inequality, if you take the left-hand side and subtract the right-hand side, in contrast with the characters, in contrast presumably with Kronecker coefficient, surprisingly that does have a combinatorial interpretation. So not everything is gloomy, and really it is possible that Kronecker coefficients might be actually in sharp P. I just don't believe so. And that's it. I've taken enough of your time. Thank you all.
Thanks.
Thank you.
Some questions? Did that previous subject have something to do with Kronecker coefficients or not?
No. So the reason why I talk about that is because that's a rare positive result.
I see.
Usually if people couldn't find the combinatorial interpretation, then they sort of give up after a while. And in this case, there is a combinatorial interpretation that was open for 30 years. It's just not a very nice combinatorial interpretation, so I can prove that it's in sharp P, but explaining what it is will take me some time. So in some sense, it's evidence against my conjecture that Kronecker coefficients are in sharp P. But who knows?
I had a question about the Littlewood-Richardson part when you were talking about the Bernstein-Zelvinsky patterns.
Mm-hmm.
Just waiting.
Let me get there. Yep.
Yeah, so I was just wondering when you used the Knudsen-Tau result, was it useful to know that there were kind of pictorial representations with these graphs, these
Yes.
trivalent graphs, or did you just use like the kind of corresponding integers that kind of like for the Bernstein-Zelvinsky you have just a bunch of integers, and for the Knudsen-Tau did you use the pictures or did you just use the integers? Do you know what I mean?
I mean, I don't really see the difference. Every picture can be encoded with integers, but yes, we did use the pictures. We essentially we needed this is the lower bound. We needed to show that there are lots and lots of puzzles with given boundary constraints. And we didn't care for specific constants, but the only way to do it constructively is by saying that yes, using Knudsen-Tau puzzles, there's some degree of freedom how you can change things around.
So you're not just using the fact that you have a bunch of integers kind of solving equations or inequalities. You're actually thinking about the pictures. Is that what you're saying?
Well, I am.
Yeah.
But computers can only do numbers, so computers would do just numbers.
Okay, cool. Thanks.
This is the first time I've seen these Bernstein-Zelvinsky patterns, but they do resemble puzzles, because whenever you have a hexagon, there's some right. The lengths of the opposite sides satisfy that condition.
This is with Ernesto Vallejo, and we have a bijection between those so from BZ you go to something called hives, and from those you can go there. It's not. I mean, each bijection is relatively simple. Putting them together is not that easy.
Yeah, understand.
So they do resemble the whole triangular shape is useful, but somehow combinatorial data comes up differently from it.
Do people think that there's kind of a pictorial representation like this for the Kroneckers, or is it just totally wide open? Nobody has any idea, or?
People definitely think that they're just wrong. I don't think there is any. That's what I mean by not in sharp P. There is no, I don't think there is any combinatorial interpretation.
Well, just because it's not in sharp P doesn't mean there's not a combinatorial interpretation. I mean, it could be I mean, there are lots of tiling problems which are not in sharp P.
I mean, I don't know if you're looking at if you look at the tiling, how do you decide if it's good, if the tiling is good for you? You're running some kind of program to decide this tiling, something matches each other, right? And running this program takes a polynomial time. So it isn't sharp P.
No. Given a set of tiles and a region, you know, finding the existence of a tiling with copies of those tiles, that's a sharp P hard problem. That's a sharp P problem. So it might be a problem of that type.
So no, I disagree. Basically, every reasonable definition of combinatorial interpretation is an interpretation which lies in sharp P. Because you have to be able to look at the tiling and decide whether it works for you or not.
Okay.
Anyway, I think we're exhausted.
Thanks, Igor. We can ask a few of us, I guess. Most people are gone, but
Thanks.
these are problems which, you know, I mean, they're adjacent to things I've thought about. I mean, I've thought about puzzles and, you know, asymptotics of Littlewood-Richardson coefficients with respect to, you know, asymptotics of puzzles. So, you know, it's something that many people I think are interested in. And,
I know.
But, you know, finding the maximum one always doesn't seem like a very natural problem from my point of view. Like, I guess I'm too much of a probabilist in that respect. Okay,
I gotta go.
All right. Bye. Thanks.
Thank you.
Bye. Thanks.
Bye-bye.
Bye-bye.